space, we can copy. So first basic approach is, why don't we? For example, if you have the 1 megabyte process, we need 1 megabyte contiguous free space. This is called the contiguous allocation approach. So in other words, it's a partition. So for example, in this case, operating system allocate occupy the beginning of the memory, and process 5 will be started, created, and the next process 8 and next process 2. Then if the process 8 is done, this will be free up. Then if the process 9 is started, always take the full, the one partition, contiguous the memory space, like this. This is called the contiguous allocation, memory allocation, the skip. Problem? It will cause make the kind of such a hole. If you create a lot of small sized process in and out, then a lot of the hole, which means it will be fragmented. So you cannot allocate the big size of the space for the big size of the process. So there are different approaches to allocate such a partition, contiguous memory space. First fit, best fit, worst fit. It's not complicated. First fit is first available chunk, okay, from the lower address. That's the first fit. Best fit is you don't want to create the big size of a hole. As less hole as possible, which means the most fitable, best fit size, the free space you can allocate. That is the best fit. Worst fit is the opposite. We'd like to create the biggest size of the free hole. Okay? So let's take a look at the example. This is our memory. So currently, H will indicate the hole. So free, free, free. And there are two running process, P3 and P4. Then if P1 is started, the size is 300. Hole 1 is the size is 600, hole 2 600, hole 3 is 400. Using first fit, which one will be allocated? H1. It's the first one. It's the first fit. Okay? So this is the first fit. Then this amount, so 300. So the other 300 will be what? The hole. Another hole. Small chunk of the free space. What about the best fit? We try to allocate the free space that create the smallest hole. This one 300. If you allocate the P1 to H2, it's a 300 free space.
Maybe
but
H3.
This one 400, so only 100. So this one will be allocated. Then it has the 100 size, another hole. Okay, this is the best fit. Worst fit is the opposite. We'd like to allocate the free space, free chunk that create the biggest hole. This one, H1 and H2, both of them create the 300 size hole. Then we can use a tiebreaker like the first fit. Then the H1, in this case the second one, but you can have the tiebreak rule to select the final hole. So in this case, the 300 will be used. Which one will be better, best fit or worst fit?
Best fit.
You cannot say which one is better than the other. Depends on. Think about the worst fit. Create the biggest free space, right? Then maybe. So for example, in this case, you cannot use the 100 size because it's too small. But if you use the worst fit, so 600, 300, 400, there may be chance to be used again. So we cannot say that this one is better than the other one. So it depends. Then, however, main problem of the contiguous allocation is like for example, P2 needs 700 byte in the memory. It's a 700 byte size process. But Is there any feasible space? No. So this is called fragmentation. So because of the fragmentation, even though we have the enough space total, free space total, we cannot allocate. So that is the fragmentation. There are two types of the fragmentation. One is external fragmentation that you know, like this one, or if you remember the old version of Windows, defragmentation. Do you remember that? Compact. That's the external fragmentation. Okay. Then, however, internal fragmentation means, so for example, we allocate the 500 byte. However, your program may be not use the last 3 bit. For example, well, 1 byte. Your basic unit is a 512 byte. Okay. So inside the allocation, there might be small chunk, a little bit the free space which is not used. That is called internal fragmentation. So this contiguous allocation definitely suffer from the external fragmentation plus also the internal fragmentation. Okay. So how to address that problem? You already know, compactation. We can pull out all the process, allocate again. Pull out, allocate again. It takes a long time, as you felt in the defragmentation, old version of Windows. Takes a long time. So fragmentation is possible, but not physical, the practical solution of that. So to address that problem, so why don't we combine similar, the chunk of that entire process as the one big contiguous chunk. Instead, divide by the meaningful chunk, which is called the segmentation. For example, think about your source code. Your source code usually have the, like in case of the object-oriented programming, it will be grouped by the object, the class. Or if we are using other program like the main program, procedure function, there might be meaningful chunk of the process part of. So we will allocate not entire the process, the chunk by chunk, which is called the segmentation, like the subroutine and so on. So we can allocate such a segment to the physical memory. At that time, just like what we did before base and limit, and also MMU, we need to know where is the starting, where is the limit, and also what is the logical address, what is the physical address for the logical address. Similarly, for the segment, for each segment, we need to know base and the limit of each segment. It's a kind of small chunk of the process, so we need to have the segment. So to manage that one, we need to have another register, segment table base register. It's the starting of each segment and size of each segment table length register. So that is managed by your CPU. It's a CPU register. Okay. So like this one, so when you read, access the instruction, first take a look at the segment part. What is the limit and what is the base? But you need to check the segment table. Where is it? It's in the memory. So this one has the address. So using the segment base table register, okay, then you can go to the memory location, then get the limit and base, apply the base and limit, the hardware, as we have used before, then check whether it's a valid address or not. In case invalid, trap or the interrupt. Otherwise, finally access the physical memory. So the program consists of a number of meaningful chunks, which is called the segment. So we can manage segment by segment. Then allocate the memory chunk segment by segment. So this is one example of the process. Process has 5 chunks, 5 segments. Each segment will be located in the different space. So we can reasonably address the problem of the fragmentation here. However, that cannot solve all the problems. Still, there are the whole which cannot be used. So it's still the segmentation, the problem. What time is it?
10:50.
Oh, sorry. So to address that problem, current operating system do not use the contiguous partition. Instead, we are going to use the paging. Idea of the paging is the same as the I/O block. Even though we have the big size of the file, basic I/O is the blocking. So block by block. So that block is in the memory. It's a page. So page is a fixed size of the data structure used in the memory. Then it will be page by page, read and write, and the I/O page by page, and so on. It's called the page in and out. So if you take a look at your resource monitor or the something documentation, you will see you need to, in case your system is lower performance, you need to check page I/O or the page in and out, because the page will determine your the performance. So next class we will continue the paging, and then we'll see how to allocate such a page. Okay, thank you, and see you on Wednesday.